Okay, so we move to the next keynote, which we move from a wider picture of what's happening in the new security world to get deep into what we do on a day-to-day basis. And it's my pleasure to welcome Ken Butler from Texas Instruments. Ken is the test systems architect in the Central Analog Engineering Group at TI in Dallas. He has been with TI for 35 years and has worked in the areas of design for testability, product reliability, analog product, test engineering, design automation, and data analytics. Ken has BS from Oklahoma State University and MS and PhD from the University of Texas at Austin, all of it in electrical engineering. He's a fellow of the IEEE, a Golden Core member of the IEEE Computer Society, and a senior member of the ACM. And many of us would have heard Ken in the other test events, but it's our pleasure to host him in ITC India. Over to you, Ken.
Thank you, Naveen. Okay, let's try again. Share the screen. Should be this one. All right, are you seeing my screen now?
Yes.
All right, very good. Thank you very much for the opportunity. I'd like to say thanks to the program and steering committees of ITC and to the ITC audience for the invitation to speak, and thank you, Naveen, for the generous introduction. I was thinking about it, and I think my first ITC was in 1990, so I didn't realize it, but I've been doing this for about 30 years, but this is my first opportunity to participate in the ITC India events, and it's really exciting to see such a large and vibrant audience participating in the conference. That's fantastic. So I'm going to talk today about managing test coverage and quality and using a very data-centric approach. So I enjoyed Deirdre's talk, and a lot of that was in and around information and data and how you manage it and how you protect it. And I'm going to be, in some ways, talking about similar kinds of ideas in this presentation. I'm going to start off also with an overview of Texas Instruments, not so much to advertise for the company, but really to kind of set the stage of some of the challenges and things that I'm going to talk about later in the presentation. So TI itself, if you're not aware of it, it started actually in the 1930s as an oil exploration company. And in the early years, they were working on seismographic equipment for oil exploration. And then in the 1940s, they got into the defense business and started taking some of their technologies and moving them into that space. And then in the 1950s, of course, everybody's familiar with Jack Kilby and his invention of the integrated circuit in 1959, which really drove the industry, our company and the industry into the integrated circuit business, which we continued on to this day. In the 1970s, there was more of an emphasis in the microprocessor technologies, and you see a picture of the Speak and Spell, which was the first application using a DSP chip for speech synthesis, which was kind of an interesting foray, and digital signal processing was a heavy emphasis of our business for quite a few years. In the 1980s, we continued the DSP. We also invented the digital light processing, or DLP technology. If you've gone to cinemas and you've seen that in the projection systems that are used to show large screen format movies, then that was a technology that came out of TI in the beginning of the 1980s, Larry Hornbeck and some other people. In the 2000s, we kind of redirected the company, and we've been more focusing in more recent years in analog circuits. We're the number one player in analog and also in embedded processing. We continue in that space to this day. We have in the early 2000s, we launched Kilby Labs, which is an applied research environment where we're developing new technologies, deploying them into our businesses, and then turning them into products for our customers. And to the present day now, where we're having a much more heavy emphasis on industrial and automotive type technologies. Here's a breakdown of the company revenue in U.S. dollars. You know, a total of $15.78 billion in 2018. With this breakdown, you know, the largest segment of it in the analog space. Still a significant player in embedded technologies, embedded processing technologies, and then $1.43 billion in other businesses. Many people know Texas Instruments for the calculator business, and that's still part of what we do, but it's a relatively small part of our business. We are much heavier into other segments. A breakdown of the markets that we service with, again, 36% as of a couple of years ago in industrial and 20% in automotive. Both of these things are growing. We still participate in the personal electronics business. So we were really heavy into the wireless technology back about 8 or 10 years ago, and it's still and personal electronics is still a large part of what we do. Communications, enterprise systems, and other technologies. Our employee population is actually larger in the Asia-Pacific region than it is in the U.S., about 12,000 in the Americas, 16,000 in Asia-Pacific, including a fairly significant presence in Bangalore, India, and 2K in Europe. But this is really the thing I want to draw your attention to, or whatever, which is the portfolio. So there's 80,000 products and 100,000 customers. So it's a very broad space that we service in terms of both products on TI.com and the customers that consume them. 14 manufacturing sites worldwide. I'm going to give you a snapshot of there in a minute, and a growing web presence where we're doing more and more direct sales of parts through TI.com. So again, as I mentioned before, we have a growing emphasis on industrial and automotive technologies, but we still participate in personal electronics, communications equipment, enterprise systems. But these are kind of the lion's share of what we're doing in the current days. This kind of gives you a snapshot of where our businesses are located. So we still have a lot of manufacturing here in North Texas. In the Dallas area. There's a list of the different fabrication facilities around here and nearby. Sherman is a facility about an hour north of us, and we have the facility that came along with the acquisition of National Semiconductor in South Portland, Maine. We still have a wafer fab and other folks present in Freising, Germany. And then in the Asia-Pacific region, we have fabrication facilities in China and Japan, and a lot of assembly test operations in various locations across Asia. And then I mentioned also that we have a significant presence in India, which is mostly a design center. So if you look at that business going back 90 years now, we were some of the early players in the semiconductor game, and maybe you didn't know it, but TI used to pull our own silicon ingots. When my wife and I started as interns in the company many years ago, she was actually working in the facility where they were pulling ingots. This is not from our operation, but if you've ever seen this, it's a fascinating process or whatever, where you have molten silicon in a crucible and you have a seed crystal, and you counter-rotate these two things and then slowly extract it and draw out this silicon ingot, which then gets sliced into wafers. And back in the 1960s, you couldn't just go and buy wafers; you had to make them yourselves, and we were involved in that process. We developed our own complete EDA toolkit. So all of the tools, again, you have companies like Synopsys and Mentor and others that you can buy them from today, but back in the early days, we had to create all those tools ourselves. We built our own wafer fab equipment. So again, there was no such thing as Applied Materials and KLA-Tencor and other companies like that back in the day. So we used to make our own implanters and reactor equipment and that kind of thing. We built our own wire bonders for the same reason. So again, you couldn't buy these things back in the early days; you had to make them. And so we had there's a building here in Dallas on the east side of what we call the North Campus or whatever, where a lot of these pieces of equipment, and including the wire bonding technologies, were actually built. We designed and built our own test equipment, and in fact, in the early 90s, we used to haul our testers to ITC and put them on the floor because we were looking to sell them to other companies. And we're not in that business today, but we still have a significant number of proprietary test equipment in production today, testing our devices. All of these things over the years have been replaced by commercial alternatives. But the point of this discussion is that we have a long history of engineering our own in-house solutions for everything, including things in the data and analytics spaces, which I'm going to really focus most of my talk on. So hopefully that gave you a quick overview of the businesses that we're in and sets the stage for some of these things that we're going to discuss in the remaining parts of the presentation here. And the thing I again want to emphasize is the enormity of scale, where we have many, many different products going to many, many different customers, all with slightly different needs in terms of quality requirements, coverage requirements, the sorts of responsiveness to their needs that they demand from us. A global manufacturing footprint where we have manufacturing operations going on literally all over the world, and we have to constantly move information back and forth in order to be able to drive intelligent decision making across all of our facilities, because there has to be a collaborative environment for this whole thing to work well. And I mentioned also that we have an automotive and industrial focus in recent years, moving into space and high-rel applications, and I'm sure many of you are engaged in these types of businesses, and so you understand that they have tremendous requirements in terms of quality, responsiveness to issues, traceability of material in order to be able to answer things like when returns happen, what was the root cause, how do we get to the root cause, what can we do about it, and so that we have to build in all the quality and the traceability into the parts to make ourselves be responsive to the customers in the market space. So to solve these problems, we take a very data-centric approach, and I'm going to talk about 4 aspects in the time we have together today. I'm going to talk about data cleaning, data democratization, breaking down the silos in between the various operations, and then I'll have the last part of the talk talking about advanced analytics and monitoring, and I'm going to get into what each one of these things means. So data cleaning. What do I mean when I'm talking about data cleaning? The idea of having clean data in order to be able to drive your operations, your business decisions, and intelligent and informed decision making about disposition of products. It seems like a simple idea. Why it should just be that way naturally. But what we find is, if you look around just a little bit or whatever, there are entire conference tutorials that I've seen dedicated just to the notion of cleaning your data in order to be able to utilize it for whatever sort of analytics you're going to do, be it business, be it engineering and technical. There are books on the subject. I haven't read this one in particular, but it looks pretty interesting to me, and I know it's something that I've had to deal with throughout my career. But there are, again, it's such an issue for so many of us in what we do that there are people that kind of focus on this very question. And it even shows up in T-shirts or whatever. I like this one in particular that says that the data scientist spends 80% of their time preparing and cleaning their data, and the other 20% of their time complaining about the fact that they have to prepare and clean their data. So what issues do we see? Why isn't the data clean to begin with? And again, there are a variety of things. These are just a few examples. We have, and certainly in our case, because we've going back to the notion of building our own systems and creating our own solutions for our own system needs. We have data sources that often weren't designed for easy post-collection and engineering analysis. We collect the data and use the information for what we have to do. So an example in the test space would be that when a tester is producing information, the most critical information that's coming off that tester is the binning information, because the binning information is going to drive all the downstream decision making about where the part goes. Does it get scrapped? Does it move on to the next test insertion? Is it a particular failure category that we need to track, and so we need to gather more information about that part, perhaps run it through some additional testing. So, but perhaps all the other additional parametric information that's coming off the tester maybe isn't as easy to get to in some cases as is something critical to business operations like binning information. We have free-form entry and which can have human error, and so that confounds things where we're looking for classifications, and I'm going to give you a couple examples of that as we move into the rest of the presentation about why free-form entry, which I think is one of the ills of some of the things that we've done in the past, it can cause us a lot of problems. Data translation errors, where I'm moving a piece of information, say from one business operation to the other, and on the course of making the translation, I drop data items, or I have issues with things like units that are conveyed from one system to the next, or whatever, that can cause problems. So these are just a few examples, but we run into lots and lots of cases where maybe the data isn't as clean and usable as we would always like it to be. So what are we doing about it? Again, I mentioned that classification is critical, and one specific example that, again, when we think about automotive and industrial and space and high rel, is that we have to understand all the information we can about our fails and what caused them. It drives quality improvement actions so we can follow up with customers. It drives and we take it from returns, from qualification failures, and from other sorts of situations, qualification things like burn-in test or whatever. So we must be able, especially particularly in automotive and industrial applications, in order to be able to get the root cause quickly, in order to explain what happened to the customers and put in corrective actions so that these things don't repeat in future manufacturing situations. Errors can be made when you're determining root cause. Sometimes you're working off limited information. You don't have enough information at your disposal in order to be able to classify what exactly the root cause was. So what we've been doing in recent years is reviewing historical data and reclassifying. So we look back at the 8D reports and the other information that was collected over the course of analyzing a part, maybe failure analysis data, physical failure analysis data, or electrical. I can't show you the categories here, unfortunately, or whatever, but we're looking for these larger bars in the Pareto of what are the kinds of things that we see multiple events that we want to go in and drive improvements into our system and corrective actions so that we don't repeat these things, particularly critical in the automotive space, as I mentioned. And we take our learnings and then we may fan these out to the businesses so that everybody starts to do these kinds of new things, be they design techniques, be they other practices in terms of the capture of information. So some of those things may be specific to particular product types. If you're building a buck or a boost or an op amp or an ADC, there may be some particular best practices that you want to implement as far as maximizing quality and minimizing cost. But other things are going to be just general good ideas. Stress tests, regardless of the kind of product that you're doing, you may be asked to do some form of stress testing as part of the overall qualification for the part. Leakage measurements, there is so much you can learn from information that comes off of leakage measurements, and I'll talk more about that when we get into the advanced analytics piece at the end. But those kinds of things maybe weren't necessarily always practiced across the board, but now we're taking some of the learnings that we have from going through this process of reclassifying failures and pushing the learning out to the businesses so that they can, add these things to their overall test flow and improve the product quality in doing so. So basically, this comes down to the old notion that we've all heard at one time or another that says you don't learn from your successes, you learn from your failures. And I was looking for some interesting quotes along those lines, and I found this particular one that I thought was particularly appropriate given the notion of looking at customer return data. Your most unhappy customers are your greatest sources of learning. And who said this? It was Bill Gates. So I definitely agree with Mr. Gates in this particular situation that we are always learning more from our failures. So we're trying to move more in the direction of having data cleaned by construction. So what do I mean by that? So this is one example that I bring up and show to you, and think of the context of a post-probe outlier analysis. So I probe the wafer, I collect a bunch of test information, and at the end of wafer probe, I'm going to take that information and I'm going to perform some post-probe analytics to look for outlier die and be able to declare certain die outliers. In order to be able to take a test, and each one of these parameters would be a particular test, in order to be able to take that information and apply it in a post-probe context, the first requirement, of course, is that I have to collect the data. And there are a lot of tests that I might collect, and where I collect the data, and there are other tests that I might not collect the data. Why would that be? Well, many test programs, at least in the analog space, begin as characterization programs where you're collecting an enormous amount of additional information about the part when you are characterizing it and trying to learn the silicon's behavior and look for things where you might have yield detractors or maybe design weaknesses that you want to go and correct in a later tape out. So we may have a test program that initially has many hundreds or thousands of parameters, but not all of which are needed for production tests. They're more for learning at the beginning of the cycle. So you may have some parameters that are named in the program but not necessarily collected in production. So the first step in order to be able to determine whether a particular outlier parameter, whether a particular test parameter is useful for outlier analysis is the data even there. So in this particular example, we can look across the good bins and all the failing bins to see which parameters are collected during production for which passing and failing categories in the die, because that's the first step to understand whether or not we'll be able to use it for outlier analysis. And this is something that is a precursor to our advanced outlier analytics solution that we have in production, where we look at all the test parameters and down select only the ones that we collect in production as the set from which we will draw outlier screening and from outlier screens that we're going to put into production. This is a different example that I saw from a gentleman at Teradyne that I saw at ITC last November, and it was a very interesting idea that they're in their case they're looking at tester configurations, and they're trying to understand which pieces of equipment, which pieces of instrumentation on their test equipment are used for which particular types of tests and for what durations, because depending on what the customer's use profile is for a set of for a type of tests and the instrumentation that are required for those tests, they could change configurations and optimize the platform for a particular usage situation by a particular customer. But what this gentleman at Teradyne, he did a poster about this. What he found was he's dealing with many customers where there aren't necessarily any standards for how they name tests. So just looking at the test name, it defies the ability to be able to categorize these things and drop them into buckets to say what type of a test it is. And if you don't know that and you can't really understand the instrumentation required behind it, then it makes it very difficult for you to go off and optimize the configuration of the platform. So he was applying machine learning types of techniques in order to be able to automatically classify tests, and he was achieving a 90% correct identification using a random forest classifier for a relatively straightforward problem of just classifying tests to understand the test content of the program in order to be able to optimize the equipment in a particular production. So those are some examples of what we're doing in order to try to clean up our data and be able to do more with it. So now I want to move on to this notion of data democratization. I thought this was a relatively new term, but I found when I did a quick Google search, I found articles that are really focused on this notion of democratization of data. And what do I mean by that? What I mean is we need to make data and tools globally available to everybody across the company. So in our case, a lot of the data that we collect, particularly in the test regime, is completely open access. So if I want to get a piece of production data from any facility around the world, I can go and grab that data and do whatever analytics that I want to. We have a fairly open system in that way. We do have some data that is restricted by business unit or customer. So there may be particular customers that we deal with where part of the arrangement is that not all the information available for the part is available to anybody in the company, but it may be restricted to people who work in that particular business or with that particular customer. And our systems, we have the ability in order to be able to restrict access like that when needed for certain situations and certain customers and products. We have a small portion of data that is a need to know, like financial data is a good example of that, where it may be highly restricted because it's very sensitive information. Markets can move based on information that might be captured here, particularly when you're talking about forecast type information. So that may be highly restricted. In those cases, there are only certain people that will have access to that data. But depending on which pieces of information you need and whether or not it's restricted, then we supply customizable tools to facilitate reporting and engineering analysis. So we very heavily use a commercial analytics tool. I won't name it here or whatever, but many of you probably have access to the same tool in your company. It has a tremendous number of plot options that are highly customizable, user customizable to generate views and reports. It has programmable extensions and links to Oracle and other databases, so you can either extract a piece of information and operate on the information on your desktop, or you can connect directly to the database and extract the information on the fly and set up reports that will pull the information periodically when you need it, anytime you need to get to it. You can also operate with the client in your machine, or you can generate a report that other people can use and drop it into a library, and then you can publish it, and then anybody can go in and use your report. And this is just a plot just showing you in the last few years, you know, we're at the point now where we're beyond 5,000 of these different reports that people have published in the library that are pulling information from a variety of sources, boiling it down, extracting information, providing reports, and it's used for all manner of business operations, production operations. Commonly used data sources can be copied to a data warehouse so that it's in a centralized location. So instead of having to work with a distributed piece of information that is captured, for example, test data that is in every single facility, you can pull that information and centralize it in one location, so that way you can look across the facility. So if you have products that are manufactured in 3 or 4 or 5 locations, then you can go off and look at it all at once, and it just makes it easier for people to get to. So the point is to make the data available whenever possible and give people the right tools to be able to analyze it. So we're working very hard to democratize information and get it in people's hands quickly so they can make the right decisions for their products. So now I'm going to talk a little bit about breaking down the silos between the various operations. So I've talked a little bit about manufacturing and test operations, and also a little bit about design. We have information that are captured in all of those places, but the challenge there can be making the information available from one part of the business into the next. So these were a couple of different similar kinds of publications. This one's external from folks at Corvo, who are up the road from us here in Richardson, Texas, and a similar kind of effort that we have been doing internally in TI. And the idea is that fab equipment for years has been monitored continuously. So there are all manner of sensors that are attached to fab equipment, to reactors and implanters and dopant machines and that kind of thing. And we measure things like chamber pressure and temperature and gas flow rate and things like that. And we have an immediate need for that because we just have to make sure to monitor the equipment and make sure that the equipment itself is healthy. But when one of these things starts to go out of control and go out of its control limits, then that can have an impact on the product. And so we need to be able to not only monitor the equipment, but also be able to react to situations before they become quality events. And so this was a situation that Corvo was looking at, where they're looking at chamber pressure and having issues keeping that under control, and so they implemented some bake lamps to try to tighten the distribution so they could get better behavior out of the equipment and minimize the amount of quality excursions that they might see. We've done similar kinds of things where we're looking for when a piece of equipment is getting substantially out of its control limits. And the difficulty here and the challenge here is that there's an enormous amount of information coming off of these pieces of equipment where you're making measurements, maybe thousands of times a second or more. And so there's a tremendous amount of data coming off here, and the signal to noise ratio is kind of a challenge, but we are making strides in order to be able to ferret out the actual true signal of the behavior of the piece of equipment and be able to understand when it's getting sufficiently out of control and intervene so that we don't generate any quality issues going to the customer. So we're working in that space as well. This is a totally different example in a completely different domain. So now think about analog product design. And we have a specification compliance matrix system that we capture this information about what sorts of things that what specifications are critical to the part that are going to wind up on the data sheet, which sorts of ones we're going to measure in verification, in silicon validation, and in production test. So it drives our data sheet systems that we publish to our customers, and it also is used for planning to determine what are the various things that we're going to do for each of the various disciplines that we use when we design a part, validate it, and then production test it. And we look at overall product coverage across all of these disciplines, and we track it across time from milestones where we kick off the part design all the way through to some intermediate review milestones, and then we get to tape out, and finally to first customer samples about what is the progress of planning for what we're going to do for each one of the individual disciplines and for the overall coverage to make sure that that coverage, we use the term coverage not the way you traditionally think of it in terms of digital coverage, stuck at 1, stuck at 0, and 98 or 99%, but coverage in terms of the specifications and where are those specifications measured to make sure that we have all of those things covered in one place or another, in one discipline or another. And we're working on plans to be able to audit our test plans against what our actual test execution against the plans that we make in this system. So we're having to kind of break down the barriers in order to be able to take the information that is part of essentially the design process, be able to relate that to test and say, are we doing an adequate job of covering the things that we need to cover, that we plan to cover as part of the overall execution of the product's development. This is a similar kind of idea that I saw published by Bosch and Teradyne about 10 years ago at ITC. And the idea was that, again, they're collecting information from test engineering, from design engineering, from manufacturing and marketing to capture a specification that's for the product. And this what they call a test specification editor, and formatted in a standardized test specification that can be used to drive test program development. So their idea here was to essentially collect all these information from these widely varying sources and standardize how it is captured with the notion of automatically generating test programs all the way out to the ATE, as opposed to essentially creating them as a manual exercise and somewhat independent of all this information that's being collected up front. So it's linking the front end and the back end together more tightly. And the notion was to sort of genericize it to the point that maybe you could have a completely tester-independent language that could be automatically translated from one platform to another. And in the 2010 timeframe, they hadn't gotten there yet, but they were working towards that goal. But it's a much tighter integration from design to test, and we see other vendors have more recently announced goals similar to that, and we TI have similar kinds of goals where we would like to essentially take the design information and rather than having design work in its own sphere and test work in a completely independent sphere, have design's information as to be essentially automatically translated into the test environment so that we have a better flow of information from the design, and it directly impacts the way that the test content is created. So it's good to see that people are continuing to work in this space, and our company and other vendors are trying to move in that particular direction. So now finally I want to get into a little bit of the advanced analytics and monitoring, because something that I've spent a lot of time on in the last number of years. So and I'm going to focus very heavily on the outlier space. That's one particular thing that I've personally had a lot of involvement in. So we've had a multi-decade journey where we've sort of getting increasingly more sophisticated in how we do outlier analysis. In the mid-1990s, it was fairly crude. It was done by lot. We would look at probe yield, and we may downgrade lots or scrap particular lots or wafers, depending if you had significant detractions in yield. And by the mid to late 90s, we were starting to move into looking at things a wafer at a time instead of a lot at a time. And we would again look at probe yield, but we started to do things like Tukey analysis, where we would look at distributions on particular parameters, look for significant outlier content, and then maybe again we might scrap the entire wafer if we have too many things that fall outside of the acceptable limits. By the late 90s, we started getting into wafer spatial rules, where we attack the wafer by looking at die, but looking at die in the context of other die. So you can think about things like surround rules and looking for things like scratches on the wafer and that sorts of thing to be able to, and use simple rules to be able to downgrade die on that basis. In the early 2000s, we started looking within die and looking at delta IDDQs and V-mins and those sorts of signals in order to be able to declare die as outliers, but still with relatively simple analytical techniques. And by the mid-2000s, we moved into more zonal regions of the wafer instead of looking at the whole wafer as an entity, to be able to treat the zones on the wafer different. And there were a variety of zones, concentric and quartiles and those sorts of things. In the mid to late 2000s, we started working on this thing with Portland State University called location averaging. They've been working on that with other people earlier in the late 90s and early 2000s, and we kind of came up with our own variation on the theme that we've deployed to production now. And since then, we've continued where we're doing die-level discrimination, die-level downgrades with enhancements to this algorithm and adding more algorithms, looking from univariate statistics to multivariate statistics, and now even machine learning. We have some work going on in that space. And we presented a paper about sort of our experience making this journey a few years ago at ITC to kind of talk about that. And the outlier solution that we developed that is our variant on location averaging, plus a few other algorithms that we have into production, we've kind of over the last few years, when we started tracking this information starting in 2011, we were working on it earlier. But when we started tracking it, there's been a huge explosion in the amount of material that we're running through the system, and we're now to the point that we're running 2 million wafers a year through this analytics solution. Again, it kind of tracks the notion that as we move into these quality-sensitive spaces where we really have to do everything we can to eliminate not only the failing die, of course, but also the ones that are at risk for future failures, early life failures, potential burn-in failures. You know, we're doing everything that we can to eliminate those die. So we're pushing more and more of our material through this system. And this is just our manufacturing operations. This is not talking about anything outside of TI. I mean, there are a couple of subcons in here, but for the most part, it's just our facilities. We've put together an outlier dashboard. So we're running this worldwide across all of our facilities. And and we could leave it to the businesses to go off and deal with the facilities on an individual basis, but we've to make things a little easier, and going back to this notion of democratized data, we have an extraction that runs every day that goes to all of the facilities where we're running wafer probe and pulls the information, aggregates it by business. So we have a table here that breaks down by each one of these rows as an individual business, where we can go, and it's a 6-month rolling view of information, so you can look at a particular time frame in a business and figure out, okay, I've got outlier rates that are running a little higher than I would like to see, so you can click on a cell here, and then you can get a program breakdown. These are all the programs that you're running in production, and maybe here's the one that has the excessive outlier loss, and then you click on that, and then you can get a wafer level drill down and a lot of details, wafer by wafer, what losses were you incurring, which parameters are the ones that are generating the most losses. So you can kind of go and dig into the details very, very quickly using that commercial tool that I talked about. So this is one of those 5,000 reports that is out there in the library that people can get to the information very quickly and understand what's going on in their products. Not only are we doing that, but we also have systems that are running in the background that are continuously monitoring that data source with push reports going out to the product owner. So if your outlier losses get to start trending in the wrong direction, then a report gets generated and sent to the product owners to say, hey, you have some material running in this particular factory, and you had these number of losses coming from these particular parameters, so they can go and react to that information and say, okay, what's going on here? Maybe we need to go and understand why these trends are going the wrong way. And the next couple of slides here, I'll kind of show you some examples of what that looks like when you follow up on that. So this was another paper that we did in 2016 at ITC, with a colleague of mine was the lead author, and so he was seeing an increased outlier count on one of the products that he was responsible for. And one of the things that we can very quickly do, given the dashboard and the information that we to provide to our users, is that you can do simple commonality analysis. Is it a particular tester? Is it a particular probe card? Is it a particular operator? Is it a particular lot that is causing the losses? And in his particular case, he identified very quickly that a particular tester was causing the majority of the losses that he was seeing. And then he started digging into the details, where you can look at the what's the solution look like, because another thing that you typically want to look at is site. This was a 4-site solution, and this was the layout of what that looks like on the probe card. It's a diagonal layout for the probe sites. And is there any commonality in site? But what he quickly saw was that no, all of the sites kind of had a similar failing signature. So you had failures across all 4 sites, so it wasn't a particular site, so it's not something where it's a probe card generated type of problem, more than likely, because you have all the sites failing sort of failures occurring equally. There were a couple of tests where he saw the signature. There were pin-to-pin leakage and an input leakage measurement that were generating the majority of the outliers. And when he dug into the details and started running some of his own DOEs, lo and behold, he sees he takes samples of measurements over a 50 millisecond time frame, and he could see a 60 hertz signal coming across here of a duration of about 200 microseconds, where every 200 at a 60 hertz rate you have this 200 microsecond wide blip. And when he finally got down to root cause or whatever, it turned out that there were vibrations on the tester. We had issues of a piece of equipment inside the test head that was causing this vibration, and at 3x the normal spec or whatever, which was generating all of these outliers. So this is really cool to me because, I think myself, for sure, and a lot of my colleagues, when we think about deploying an outlier solution, you think about it as looking for bad behavior in the silicon, but just fairly frequently it will be not the silicon itself, but the test solution that is causing the problem, be it the hardware, the tester itself, some of the instruments inside the tester. And when you go off and make a corrective action like this by correcting this problem, not only does the immediate product that you were looking at benefit, but all the other products that run across that platform achieve the same benefit because it was probably impacting all of them, and this was just the first one that got tracked down. So, in summary, we need excellent coverage and quality for our particularly for automotive and industrial spaces, space and high-rel, and it requires collaboration across all of our disciplines. We have to have accurate, timely, and readily available data, and data, not just raw data, but turning it into information, cleaning it up, simplifying it, aggregating it, summarizing it so that people can make the right decision-making. It has to be integrated across design, verification, validation, and manufacturing. All of these things have to come together because you need to be able to see all of it in order to get the clear picture and the true picture of what's going on. And you have anywhere from engineers all the way up to C-suite executives and all levels in between that need to be able to look at that information. And finally, we need advanced analytical methods that will be a requirement. We've done a little bit of that on our own. We're starting to get into this notion of machine learning. I see a lot of work going on at this conference and at previous conferences, and we think that's great. We want people to continue to work and invest in this space because we think that those solutions are definitely going to be needed. So thank you very much for your time and attention. I really appreciate it. Again, it's an honor to get asked to participate in the conference, and I'll stop now and take questions.
Thank you, Ken. We have one question to begin with. This is from Sriram. He's not mentioned his affiliation, but in view of the Keynote 1, data democratization seems prone to side channeling and security breaches. How shall it be managed?
I'm sorry, would you say it again? I didn't quite hear exactly what you said. I apologize.
Sure, no problem. So this is with reference to Keynote 1.
Yes.
I mean, what was mentioned in Keynote 1. Data democratization seems prone to side channeling and security breaches. How should that be managed?
Well, and that's, and Deirdre talked about that, and she mentioned in her talk that scan information can be used, for example, to reverse engineer a product functionality, and that's critical. Typically, the kinds of information that we're getting to is maybe, in some cases it may be down to that level of detail. There's a lot of things that we can do at higher levels of granularity where maybe the product functionality isn't at risk. But the main thing that we have to do is we have to guard our information to make sure it doesn't get into the wrong hands. So we have a very strong firewall where we hold the information, and anybody inside of our company can get to it, but anybody else is going to have great difficulty in getting to that information. And sometimes it can work against us in the fact that when we do deal with subcons where they collect all the test information, for example, if we're working with a test house, sometimes it can be very difficult for us to be able to get that information because, again, they have the responsibilities to protect it for their customers, including us. And so we have to kind of figure out ways to be able to secure the information, get it to people when they need it, but keep it in-house when you must in order to protect it from prying eyes. And I think people are working on security mechanisms in order to be able to encrypt the information so that it's an outside party, it's meaningless to them, but for an inside party with the keys, they can be able to do the right things they need to do with it in terms of yield enhancement or whatever.
Thank you. Kavita, is there another question?
Yes, there's one more. This is from Tirumalesh. How effectively can machine learning aid in adaptive-based ATE testing, thereby reducing testing cost? Is from NXP.
There are lots of applications for that. So one thing that we took a look at was essentially predictive analytics. So one of the things that is done, if you're familiar with it in wafer manufacturing, is what you might call parametric test, or e-test, as some people call it. And today that might be 21 sites across the wafer where you collect information from structures in the scribe lines that give you some, and you make performance measurements. You may measure transistor gain or sheet resistance and things like that. And you can, when you take that information, you can start with machine learning type approaches to be able to get an idea of a rough view of the wafer map even before you've done any wafer probe type operations. And you can use that in an intelligent way in order to be able to steer test content, so maybe certain portions of the wafer will get different test content, or the types of tests that will be applied will be different than other portions of the wafer based on an intelligent pre-processing of e-test data in order to give an early look at what the wafer map looks like and where are hot and cold regions of the wafer, because wafer variability with 12-inch wafers, and in our cases very small die size, within wafer variance can be enormous, and so we're looking for intelligent ways to be able to do that. And that's just one example where you can apply machine learning type techniques in order to be able to enhance the overall test operation.
One last question, Kavita, before we wrap up.
Yeah, there's one more. If you can track down to an individual operator, there seems to be a big brother aspect to your system. Any opposition? This is from Eric.
Well, it's, you know, an operator is not something that I use that as an example, but it's not necessarily something that happens all the time. But the fact of the matter is, when you working in a production test facility or in a wafer fab, you go through these things called log points, and every time you get to a log point, the very first piece of information that's collected is who's the operator that's performing that operation. It's not necessarily Big Brother looking over your shoulder so much as, you know, if there's something that the operator is not doing correctly because maybe they haven't been trained appropriately or whatever, then you need to be able to react to that and provide them the right information to be able to do that step as needed. But it's not really but it's not used in a punitive way. It's more to just make sure that we're doing the right things by our customers. And if we have folks that have the wrong information or maybe doing something in not quite the correct way, then we can track it down and correct it. But that's always collected. I mean, in any step, the very first thing that you're going to find out is who is the operator that's responsible for that step.
Okay, I think that's all I have, Naveen.
Thank you. Thanks, Ken. I took over the control over the slide, but I've heard you a couple of times, but it was really good that the wider audience could get to hear about all the work where you showed the history from multiple decades and then connected to what you're doing now. That was very helpful. On behalf of the whole committee as well as participants, I would like to thank you. I know it's late Sunday night, really late night, maybe midnight already for you. Thank you for taking time and ensuring you share your experience and thoughts with us. We appreciate that.
Thank you so much. I'm very much honored to get this opportunity to do it. Thank you so much to you and the ITC audience.
Sure.